Yeah, so glad you guys are here. Welcome to the review session for our midterm. I know you guys have all been following along on Canvas. You probably are up to date about what's coming up. There is homework due tonight, Sunday night, by midnight. I do have, after the review session, I'm going to give myself a break for a little bit of time before I go into office hours tonight. But I will be having office hours and be happy to take questions about the homework as well as just anything in your studying that you're doing. Hopefully, you're gearing up to try one of the sample tests uh, for the midterm. I would recommend that if you haven't done a sample test yet, I would recommend that you try one um, after this review session sometime. You should be pretty well primed up for it, I think, after today's review. So I'm hoping that you'll be able to do that. What I'm going to do in the review primarily is a bunch of practice problems, kind of in a random order. I'd like to go over a couple of problems off of the group works that we didn't have time to do in class. I've come with a couple of other questions that I thought might be useful to go over as well. And at some point, I'm going to probably pull up that extra credit quiz that we took and kind of talk through that as well. But there's basically four parts to this material, which are the four chapters that we've covered. So, we have chapter 6. Well, it's specifically 6.3 and 6.4. This is the material about a kernel of a transformation and range of a transformation. Then we have the whole question, is it one-to-one? Is it onto? Is it both or is it neither? And of course, if it's both, we've seen the word isomorphism associated with that. So you'll want to, if you go through the review packet for the midterm, you're going to see all of these words are in that packet. They're all listed out there. And so it wouldn't be a bad idea to go back to that packet and just kind of go through, make sure you know what all these words mean. I may not review them all in total detail right here, but of course you guys should ask questions during this review. So if there is something you want me to expound upon a little bit more detail, just let me know because I'm in no hurry. And the whole point here is not to rush through this, but rather to really try to make sure people are solid on it. So all of this stuff, this is going to be somewhere around 20 to 25% of the exam. Also, I should mention the general rank nullity theorem. This is really important. The dimension of the kernel of T plus the dimension of the range of T, right? We all know that adds up to the dimension of V. That's one of the most important equations that we work with in this section of the course. It helps us to, appreciate the relationship between the kernel and the range a little bit, at least with respect to how big they are. Because if I'm asking you to give a basis, very common question, find a basis for the kernel, find a basis for the range. Well, if you know their dimensions, right, or if you can say something about their dimensions, that will help you with figuring out a basis because you know how many vectors should be in your basis in that case, right? So the dimension is really important, and we have this nice, easy equation to help us make a relationship there between those ideas. So that's kind of the first part of what we need to review, and this is older material, right? This takes us back at least a month or so. So if it's not so fresh in your mind from recent times, then I would definitely give this some attention, okay? But then we moved into chapter 7, and we looked at the first 3 sections of this chapter only. This is all about, of course, eigenvalues and eigenvectors. And so this is where we have the lambdas and the v's that are associated with our matrix. Of course, in this chapter, all of our matrices are n by n. So we're only working with a square size matrix A in this case. And what we're doing is we're finding eigenvalues and eigenvectors. A couple of really important equations here. Again, I'm not going to do a full-blown review, but I guess I'm hitting a couple of the highlights. The most important equation in this entire chapter, I've talked about it so many times now, just to re-emphasize it again, A times V equals lambda times V, right? If there was only one thing you knew about eigenvalues and eigenvectors, I would want it to be that. That this is basically saying that when you take your vector V and you and you multiply it by the matrix A, the effect is to just stretch the vector by this stretch factor of lambda. Which could be a negative number or it could be a fraction, right? It doesn't have to be a positive number necessarily, but that's one of the very important equations, probably the most important one. But then don't forget about another very important equation here, which is the characteristic equation. The characteristic equation, this is the one where we do the determinant of A minus lambda I, and then we set that equal to 0. So just to remind you again what this is used for, I know you guys are doing this a lot, so we probably don't need to dwell on it too much, but this is the equation that we use to find the lambdas, to figure out what are the eigenvalues of our matrix. So we find those eigenvalues using the characteristic equation. And then the corresponding eigenvectors are going to come by, which are the v vectors, right? These are going to come from looking at the null space of the quantity A minus lambda I. Right, so this goes right along with the characteristic equation. Hello, everybody. This is a good turnout. I'm happy to see everybody coming in today. Wasn't it nice to just pull right up and park in the front row? We don't usually get to do that, but today we got easy parking and good weather and nice day to kind of do some review. Right, so, when we're talking about this section of the course, which I would say is probably another 25% of the material here, you're talking about finding eigenvalues and eigenvectors of a matrix. And the key ingredients to doing that are going to be this characteristic equation and then these null spaces. Okay, so I can't overemphasize, how many times have we found a null space in the last few weeks? Oh my gosh, I can't count all of the times on my fingers or toes combined, right? It's way more than all of that. Yeah, so a lot of times. Okay, and then, one of the big concerns that we have with this eigenvalue, eigenvector theory is whether or not we can diagonalize our matrix. Right, whether it is a diagonalizable matrix or not, yes or no. This was what was on the extra credit quiz. I gave you a matrix and I asked you, is it diagonalizable or not? So this all comes down to whether the matrix has eigenvalues that pull their weight, right? So, so I'll just put this here. Is it defective or non-defective? This is a big question that we like to ask. Non-defective, just to remind you here, this just means that the multiplicity of each of my lambdas, I write that as m sub lambda, it should match the dimension of the eigenspace. By the way, the eigenspace E sub lambda, that is just this null space of E of A minus lambda I. So when we talk about the eigenspace, it really is just this null space here, and it's going to have a certain dimension. And for a matrix to be non-defective, then for every one of our lambdas, for all of the lambdas, right, the dimension of the eigenspace should match the multiplicity. The way I like to say that casually is just that every eigenvalue should pull its weight, right? Every eigenvalue should pull its weight. And if that's true, then the matrix is non-defective. Right. And in this non-defective case, just one last point of review, and this is important because I didn't really ever actually lecture on this. You guys watched a video about this part, but in the non-defective case, right, we can actually diagonalize the matrix. So I'll just remind you that we have these equations, S inverse AS equals D, right? So we have this relationship here. And just to remind you, this is where S is the matrix where we put the eigenvectors. I'm just going to label them as columns here, V1, V2, up to Vn. Those are the eigenvectors of the matrix A. They can be put in any order that you want. Okay, there's no requirement on that, as long as when you write down the matrix D, remember that D is the diagonal matrix where all of the lambdas are just listed right down that main diagonal. You just have to make sure that your lambdas and your V's are lined up correctly, right? So whatever order you put the eigenvectors in, then the eigenvalues should be arranged in the same compatible order. That's the idea behind that. Is this all looking familiar so far? Okay, so this is chapter 7, and I put it as 25% of your exam, but honestly, we really should be thinking of it more like 40 to 50%, because remember that when we get into chapter 9, which is the very recent material we learned, right? Almost the first thing we have to do is find all of the eigenvalues and eigenvectors of whatever the coefficient matrix is for our system of differential equations. So this stuff is important in its own right, at least for a quarter of the exam, but probably for a whole nother quarter of the exam, we need it in order to even be able to solve those systems of differential equations. So I really think it's worth emphasizing this this point here, or this little material. Guys, all I'm doing, for those of you who just came in, I'm just giving a quick little overview of what's going to be on this exam. I'm not going into a lot of details on this yet, because I want to focus on practicing the material with some examples in a little while. But at least for now, we have, just a quick summary for you. So that's a nice summary of the highlights of chapter 6 and 7. And that's about half of what you guys need to be studying for our exam. Okay, then we kind of changed gears, right? I'll come over here to talk about the next piece of this, which is chapter 8. And we have 4 sections here in chapter 8. And in this chapter, all of a sudden, we lose the vectors and the matrices, and it's all just back to solving nth order linear differential equations again. And you'll remember that I wrote it in this very abbreviated form, L of y equals f, right? And the goal here, as you know, the goal was to solve for y. And I gave a 3-step process for this, right? So there were sort of 3 parts to doing this. And just to remind you again briefly, the first step of this solving one of these problems, by the way, what is this going to be? This is an nth order. This is an nth order linear differential equation. That's just kind of the standard form. It's a very compressed form of how we could write it. And the first step to solving this thing is to ignore the capital F and just solve the corresponding homogeneous nth order linear differential equation. And when it's homogeneous, it just means is equaling to 0 on the right side. And when we solve that, we're solving for what was called the complementary function. So just to quickly put that down again here, we're going to solve for the complementary function, which is y sub c of x. Okay, and I would always recommend when you're doing these problems, put that thing in a box again, okay, so that we can find it later. In step 1, we find this complementary function. It's a simple matter of writing down the auxiliary equation for the difference. So you basically, this L operator just involves d, the derivatives d of your unknown function. And you just turn all those d's into r's. That gives you this auxiliary equation. And then you just have to find the roots of it. And your job is to just remember, what are you going to do based on those roots? The roots could be repeated. They could be complex numbers. So you have to remember some of that. I'm not going to go over all the details right this moment. but with enough practice, that's pretty routine. Okay, it's pretty routine. Actually, to me, the hardest part is just factoring the auxiliary equation correctly. My goal is not going to be to trip you guys up with polynomials that are impossible to factor, right? I might even give you a factored type of operator to begin with, so you don't even have to sweat that piece of it. But you should be able to factor anything that's a quadratic for sure, because we all know how to use the quadratic formula. And even if it was something a little more than a quadratic, as long as it was relatively easy, kind of clear what to do by hand, maybe factoring by grouping, something like that, you probably, I would hope that you could do that much at least. Okay, so by hand. But anyway, that's really the main work that goes into step one. You just have to be able to find that auxiliary equation and get the roots from it. Then step two is where we find we find one particular solution, right? One particular solution, and I'm going to write this as y sub p of x, right? And there are, I'll put a little asterisk here because there are some things I want to say about this step two in a moment. But once we've come up with the particular solution that we're going to use, then step three is just the final answer. And this is very easy as well. You don't really have to do anything here to write the general solution, right? Just to remind you, you're simply going to go ahead and write y of x equals y sub c of x plus y sub p of x. Right, so there would be your final answer, okay? If you have put nice boxes around steps 1 and 2, and because sometimes they can be kind of long. You guys might remember in class, I think I did a 14th order differential equation one day, and it took like half the board just to write down the answer. You'd hate to have to recopy it all down a second time in step 3. That might be 5 minutes that you'd rather spend doing something else. So if you put boxes around these pieces and you're going along, I'm totally okay as long as I can find your work, right? Make it easy for me to find it when I'm grading it. As long as I can find your work, if you just want to kind of remind me here what you're going to do with those pieces at the end, I'm good with that. Okay, so you can save a little bit of writing at that point. So this step 2, I'm going to now talk about the asterisk point for a second with you guys. There are 2 methods that we learned for how to do the particular solution. Does anybody remember what they are? Liam?
There's the variation of parameters method and there's the annihilators.
You got it. There's the annihilators. I'm going to put that one first because that's the one that we learned first. So we have the annihilators method. This is where we use the A of D, right? To annihilate the capital F that's up here on the right-hand side. That's one method that we learned. And then there was a second method. And again, I did not lecture on this, but had you watching a video on it. So this was called variation of parameters. The variation of parameters method requires you to remember a couple of formulas. So and again, I would rather have you learn these formulas and I can give you partial credit for knowing them rather than just giving you these formulas. They're not that hard to learn, but there's a U1 and a U2 that are based on doing integration here. So we might have something like this, U1 being negative the integral of y2 times f all over w, and U2 is positive the integral of y1 times f all over w. These are the variation of parameters important formulas, because what you do then is you write down your particular solution, in this case as U1 times y1 plus U2 times y2. And just to remind you again, the y1 and the y2, those are coming from the complementary function. There's going to be 2 terms in that complementary function, and we would label those as y1 and y2, and then use them to solve for u1 and u2 and write down the particular solution here. Again, guys, for those of you who just came in, I am not in a hurry with this review. Like, I totally want you to ask questions. Anything is not clear, just shout it out, let me know what I can help with here. Somebody did ask me in my office hours earlier today, does it matter what order the terms of your solutions are written in? Like you have C1 times one solution plus C2 times a second solution plus C3 times another solution. Does it ever matter? Because you check your answers against my answers, you might have written them in a different order. Of course, we all know though that right when we add things together, it doesn't really matter what order we add them in. So it makes no difference. So if I have a y1 and a y2 coming from step one, and Liam has them in the opposite order as his y2 is my y1 and his y1 is my y2. Are we going to get messed up down here when we're doing the u1 and the u2? Well, of course, we're going to have different expressions here for what we're calling u1 and u2. But at the end of the day, when we settle the dust and we write down the whole particular solution, we may have our terms listed in a different order from one another, but we can both be correct, and we both will be correct, assuming that everything else is correct. The order of the terms doesn't matter, okay? So this variation of parameters thing is not too difficult as long as you know the formulas. You have to remember that there's a minus sign on the U1 formula. You have to remember that the subscripts are swapped between, the U1 involves the integral of y2, the u2 involves the integral of y1. So I just remember that they get swapped. Both integrals require dividing by the Wronskian. And the other thing I wanted to mention about the variation of parameters here is this is going to be for second order only. So if your L of y equals f, if your operator up here is a operator of order 3 or more, then you're not going to be doing variation of parameters. It's not that you can't do it. It's just I didn't teach that. I only explained for you guys how it would work for a second order equation. The reason being that the formulas for the variation of parameters in a higher order situation, it's just too hard to do it by hand, right? It's just too hard to do it by hand. So we tend to just, for the purposes of this class, we're not going onto a computer to solve anything. The basic idea behind it can be pretty clearly understood just from a second order equation. Yeah, Audrey? Uh-huh. The integral of sine of x times the tangent of x. Well, cosine x times tangent of x, I would definitely expect you to be able to do.
Then it was sine of x.
Okay. Right, this is the harder one.
Yes.
So, I really try my best in this class to not make things come down to whether we can do the integrals or not. But of course, we have some kind of prerequisites for this class. So my trick whenever I teach calculus, what I always tell my students about everything in trigonometry for calculus is turn it all into sines and cosines. And so in this case, I would take the tangent and rewrite it as sine over cosine, and then try to figure out how to do this integral. This one can be done by rewriting sine squared as 1 minus cosine squared. You're asking me one that's really on the cusp of what I think would be reasonable. This one isn't too bad. If I now split up the numerator, 1 over cosine would be secant, and cosine squared over cosine is just cosine. And I can do this integral. Secant is in the table, and cosine is, the integral of cosine is just sine. So I might be asking for trouble for this one, but I will be trying to hope that my students could do it. If people mess up integrations, but everything else is correct, they obviously know step 1, step 2, step 3. They've written down the U1 and the U2. They know what the Wronskian is, all that good stuff, right? You can imagine that on a 10-point problem or something, getting to this stage and then fumbling up the integral here is probably only going to cost somebody maybe a point or two. It's not going to be something where studying for 500 hours for this exam is going to make any difference. It's not going to be worth worrying about. So I wouldn't get too bent out of shape on it. I do not think for most of us that the game plan for the weekend should be, oh, I'm going to go back and review all my integration again. No, no, no. It's not what 250B is about. It's not what I really want you guys to focus on. Okay. So anyways, yeah, this one is kind of on the fringes of what I would want you to be able to do. But yeah, the downside of variation of parameters is you've got to be able to do a couple of integrals. Okay. The annihilator method, you don't have to do that. Okay. So why wouldn't we always just use the annihilator method? Liam?
Because sometimes we don't have the annihilator.
Exactly. We don't know the annihilator for every single possible f of x here, right? So if we don't know how to annihilate f of x, then we need to be thinking about maybe variation of parameters instead, especially if it's only second order. That would be consistent with what I've told you. Now, if I gave you a third order differential equation where we didn't know an annihilator for it, then that would be my bad. At that point, it would be on me. I've asked you a question that we don't know how to do the annihilator method, and the differential equation has an order that's too high for what we learned as well. That would be on me. I didn't ask a question that was lined up with what we've learned. So you have to trust me that I'm going to do a good job on that. Anyway, this is another maybe 25% of the test. It can take a while to do, especially step 2 here. Okay. You guys probably remember for the annihilator method, you write down the form of the particular solution, but it might have constants like A or B or C in it. Do you remember that? Oh, finding those constants can be a page worth of chicken scratch of calculating out what those coefficients are. Please don't spend like 20 minutes or even 15 minutes trying to solve for A, B, and C. It's not going to be worth very many points. It's not worth it. I would just, first of all, I might say in the question, I might just say, don't bother to find the constants, right? I might just say, give me the form of the particular solution. If I ask it that way, then you know I'm basically telling you that I don't need you to solve for the constants in the particular solution. And so save yourself a lot of headache with that, right? And then even if I do ask you to find the constants, it's probably going to be something where it's really easy and not supposed to take a lot of time. And if somebody were to mess it up, as long as I could tell that they kind of knew what they were supposed to be trying to do, I probably wouldn't take off more than a point or two. Again, on like a 10-point problem, it would be worth a very small piece of this whole 3-step rubric here that we've got. Yeah, Marcus?
You just put a particular solution into the original.
Yeah, you take the form of your particular solution and you plug it back in on both the left and the right of this, and you match up the terms on the left with the terms on the right, which should give you equations to solve for those constants. And if I'm doing a good job of writing my test, those equations would be relatively tractable. They shouldn't be, insane. First of all, it shouldn't be very many constants, and it shouldn't be like too many derivatives here, right? If L was a 14th order derivative operator, then strictly speaking, to solve for the constants, you would have to take 14 derivatives of your trial solution. Well, that's not probably reasonable for an exam. So you have to trust me that I'm going to rig my problems. Well, you can look at my sample tests to see, well, what kind of what's the level of what kind of problems am I going to see in terms of solving for these constants in the particular solution. And that's what I'll be shooting for. Okay, so that's kind of the third chunk of it. So we've got chapter 6, chapter 7, chapter 8, and then finally chapter 9, which is what we've been doing most recently. 9.2 through 9.5. And here is where we're working with this linear system of differential equations. So we talk about x prime equals ax again, right? And so the A in this chapter is always a square matrix. And again, the goal this time, right, is to solve for the X. Solve for the X vector. That's what we would be looking for in this case. So you guys can all figure out the math. This is going to be maybe another 25%. Okay, so all four of these chapters, kind of thinking of them as 25% each. At its core, the basic idea here is to come up with solutions x of t that are of the form e to the lambda t times v, right? And so this involves finding the eigenpairs, which are the lambda and v pairs that we could have, right? So we look for those eigenpairs of the matrix A. Right, and so this is what that would look like, the lambda and the v eigenpairs. We do know that it's possible that these eigenpairs could involve complex numbers. So we did see that sometimes we have to use this Floyd technique, which is actually on the homework, the most recent homework now that we're working on for tonight. The Floyd technique, we talked about it on Tuesday. It's how we extract real solutions in the case when these eigenpairs involve imaginary numbers. The other big hiccup that we ran into was that in some cases, the matrix being possibly defective could get us into trouble, right? If the matrix was defective, then we're not going to get n eigenpairs here. Remember that the matrix is n by n, and so the solutions for x here should form an n-dimensional vector space. That means I need n solutions. Well, if the matrix is defective, then we don't just get n eigenpairs straight away, right? Or at least not n linearly independent eigenvectors. So in that case, we had to modify the solutions, and that's where the stuff we just learned this past week comes into play with those W's, right? The W1 and the W2. And if the matrix was super defective, that we've talked about on Thursday, then you would actually need a W3, W4, and W5 as well as an even more complicated situation. But anyway, so the 90% of what's in this chapter is really just solving these linear systems of equations, right? There's some other things we can do. We talked about phase portraits, drawing the pictures. Are we looking at a saddle or a source or a sink? Or is it a spiral, either a stable or an unstable spiral, or potentially just a circle? So there's those 6 outcomes that are just based on what the eigenvalues are. We in passing talked about that briefly, but mostly what this chapter is solving for x in this system right here. Generally for 2 by 2 and 3 by 3 matrices, that's generally what you're going to see. Probably not a lot bigger than that. So I'll leave it at that for now. This is, of course, the more recent material, so I'm not going to give a whole lot more details at this point. Yeah, Julie?
The phase portraits,
Yeah.
we need to draw to identify them.
Would we have to draw the phase portraits, or would we have to identify the phase portraits? I guess I could ask it either way. You've never really had to draw any other. I think there's one homework problem for tonight where you have to draw the picture of the phase portrait at the very end of the assignment, but there's not a lot of drawing them. The reason I don't like drawing them is because everybody draws differently, and it wouldn't be fun to grade, put it that way. When you look at my sample midterms, on one of my sample midterms, I have a matching exercise. So I have a bunch of matrices and I have a bunch of phase portraits, and I just say, well, which system would go with which phase portrait? And that made a really good test question because I could just easily grade it, and it, I think, got the point across. So yeah, I've not written the test yet. As you guys all know, I always write my test at like the absolute last minute. So I like to do the review session first and not think about what I'm going to ask you yet. But yeah, I don't know how I'll end up doing that, but I'd be surprised if I have something about face portraits on there. It's a possibility. Probably not a lot of points for that, but it could be something about that. Definitely. So this is my overview. I want to start doing some actual problems now, but does anybody have any questions about the overview of what we've got here? one reason I like to do the overview is, you know, if you hear some word comes out of my mouth, it's like, oops, I don't remember that. Or something, you know, just triggers a thought in your head of what you need to maybe review or a weak point. Sometimes that can come out if we kind of talk through all of this stuff. But really, guys, chapter 7 and 9, they really go together, and that's 50%, right? To do chapter 9, you're going to need to be able to find these eigenpairs. And also, I forgot to write it down, didn't I? The fun facts. Everybody knows the fun facts, right? I didn't used to teach those. I used to just let people try to get the lambdas right. But now we have this nice set of fun facts. If we add up the lambdas, this technically goes in chapter 7. I should have put it over here. If we add the lambdas together, we get the trace of the matrix. And if we multiply the lambdas together, we get the determinant of the matrix. So don't hesitate to check your lambdas to make sure you're getting them right. It's super important. Did you have your hand up?
Yeah. for
Please.
Chapter 7, are we gonna have to know Markov's process?
Markov's process, probably not. We didn't do any homework on it. I know I had you watch a video section about it, and there is one problem in the old review packet that's about that. But I don't feel like I did enough with that with you guys to expect you to be able to sort of put all that together. And it really isn't part of the syllabus for this class. That was kind of an extra. Why did I even talk about it? It's just I wanted people to understand why the diagonalization process could be useful in the real world, as opposed to just we're monkeying around with linear algebra here. It's like, what's it good for? But it really would be better placed in a different class, I would say. Yeah, we have enough material. Unless anybody wants the Markov processes to be here, I think we'll just let that slide for now. Everybody's good? Okay. I think it sounds like people don't want to see it on the test, so we'll try to leave it off the test. Okay. Yeah, so I thought I might just throw some examples at you. I mean, one of the things about taking a test with 4 chapters of material is the problems are kind of going to come from all different parts of this. I guess you could call it a syllabus for the exam. And so you have to be ready to kind of address whatever comes your way. So let's just start doing some example problems. And I'll just number them kind of in order here in case we want to refer back to this later. But let's see if we can do the following problem. Let's find the general solution to, and then I'm going to write it down, x1 prime equals 8x1 plus 8x2 plus 8x3. And then x2 prime is equal to 8x2 plus 8x3. And then x3 prime is going to equal 8x3. We're going to make this as our linear system. Ooh, I kind of gave it away already. And we have to figure out, is this from chapter 6, chapter 7, chapter 8, or chapter 9? Like where in the 4 parts of the exam that we're covering here does this kind of problem fit into the material, right? And what you notice here is that we have more than one unknown function, right? There, we see the derivative of x1, and we also see the derivative of x2 and of x3. So all of those derivatives are there. That suggests that we're looking at a system of differential equations. This is not just one differential equation, it's an entire system of differential equations. So does anybody want to suggest how we might, so which of the 4 chapters does this seem to be related with? Liam? Stuff right here, isn't it? Yeah, it's just a linear system of differential equations, exactly. So what might I want to do first? Audrey? Put it in a matrix. The running joke of Math 250B, the answer to everything in this class is put it in a matrix. Exactly. So on the left side, I'm just going to abbreviate that as the vector x derivative, right? So the derivative of the x vector. Then we're going to have a matrix here that's multiplied by x, right? This is the way the form should look. And these numbers that are the coefficients of the system here, right? They just go straight into the matrix. So the first row, I have 8, 8, and 8. The second row, I have 0, 8, and 8. And the third row, I have 0, and 0, and 8. It's going to look just like that. And so this is my capital A right here. Yeah, that's my matrix. Capital A, it's 3 by 3. And so the goal is to solve for x, as we know. And the strategy for doing this is to find the eigenpairs and put together these solutions here. Do we know what the eigenvalues of this matrix are without even taking a breath? Audrey?
It's 8 times.
Exactly. And how do you know that?
It's the-
When you have a triangular matrix, the lambdas are right on the main diagonal. Okay, we could, if we didn't know that, if we didn't remember that, it's okay. We could just write out the determinant, right? We could do the determinant of, 8 minus lambda, 8 and 8, and 0 and 8 minus lambda and 8, and 0 and 0 and 8 minus lambda. But we know that the determinant of a triangular matrix is just the product of the diagonal entries. So this would just actually be 8 minus lambda being cubed at this point. Yeah, go ahead.
Is that the same for lower triangular matrix?
Yeah, same thing for lower triangular. Absolutely the same thing for lower triangular. Exactly. And so when we set that equal to 0, right, then exactly as Audrey said, we get lambda equals 8, 8, and 8. You can be sure to write down repeats because that's always a big deal in terms of the theory of the eigenvalues and eigenvectors. So there's my lambdas right here. So far, so good? So once I know the eigenvalues, then my attention is going to turn to finding the eigenvectors that go with those eigenvalues. So here's where I'm going to do the null space of, I need to take the matrix that I get when I subtract 8 from the main diagonal. So I'm going to get 0, 8, and 8, and 0, and 0, and 8, and 0, and 0, and 0. This is going to be my null space matrix here. And it's basically in row echelon form. We could divide every row through by 8, and we're basically going to get pivots that look like that. And based on what I've got here, does it look like the eigenvalues are going to pull their weight? This has a weight of 3, right? And if I think about my unknowns here, the x, y, and z unknowns that we have, how many free variables do you see there?
1.
I only see one. I only see one free variable, which is the x variable. So z is actually 0 and y is actually 0. And the only free variable, which I'll call it t, is just x. Exactly. So that's it. And so when we bust out our variable there, we're just going to get, when we bust out the t, we're just going to get the vector 1, 0, 0. That's the only thing we're going to have there. So if this eigenvalue didn't pull its weight, it tells me that the matrix is defective. And what kind of defective are we talking about here? I know we just learned this. Is this mixed eigenvalue? Is it regular defective? Or is it super defective?
Super defective.
Super defective, right? Is that what you guys were going to say? Super defective. This is super defective, right? Because I only got one eigenvector, even though the same eigenvalue showed up 3 times here. So I'm totally expecting this to be super defective. So we have to remember how to create our solution. We still have to come up with 3 solutions, right? Even it's a 3 by 3 system. So the solution set is a 3-dimensional solution space. I've got to get 3 solutions. I know that I can make one of them. I'm going to go ahead and do it now. I can make one solution directly from the eigenvalue eigenvector pair that we did find. And here it is right here. This is the x1 of t. So I can get that pretty much straight away from the work we've already done. But now we have to figure out the rest of the x2 and the x3. So I'm just going to remind you here what the formulas are. And this is just reviewing from this Thursday, because I know we just learned this. This is also what's on the homework that you're working on for tonight. In this case, the second solution is going to have the form e to the lambda t times w1 plus t times w2. Okay, you guys are gonna need to know these. So put these on your flashcards if you're not sure. I know it's only been a few days that we've had this down, but you will need to know this for Tuesday. Each of the solutions has e to the lambda t in it, but this third one, the super defective case, involves W3 plus t times W4 plus t squared over 2 times W5. We just have to learn that. Remember, this is something that I didn't come up with. This is somebody figured out that by putting these forms down, that they could get valid solutions to our system. And the key thing to help us with the W's is this diagram, which is not in the book. Oops. I'm going to do the W3 diagram first. So we're going to choose W3 in such a way that it survives A minus lambda I once, which turns it into W4. And then it's going to survive A minus lambda I again, which is going to turn it into W5. And then it's going to not survive 3 times. So as soon as I get to the third arc of my diagram here, it's not going to survive that diagram. Okay. And there's a similar diagram for W1 and W2, which I'll kind of lay out here underneath. The thing is that with the W1, W2 diagram, there's no reason why you can't just line these up. You don't have to do this. You don't have to choose W1 and W4 to be the same, or W2 and W5 to be the same, but you can choose to do that, and it just makes your life easier, I think. Okay? The big thing is choosing the W3 correctly. This may be the hard part. How are you going to know what to do for W3? You have to choose, there's many right answers, but you must choose it in such a way that it will survive 2 powers of A minus lambda I, right? But will not survive 3 powers of it. So if I get stuck at this point in the process, this is kind of where the new material is. If I get stuck here, what I generally do for myself is I literally just start writing down, okay, what is A minus lambda I? And then what is A minus lambda I squared? And then what is A minus lambda I cubed? I just want to try to calculate all of these. Okay, so that's what we would need to do. And I'll just show that here. And so A minus 8I, by the way, that is actually just this matrix here. Okay, so if you subtract, here's the A, right? If you subtract the lambda from the main diagonal, you're just going to get 0, 8, 8, and 0, 0, 8, and 0, 0, 0. And if you square that matrix, so if we square that matrix, so we're going to write it down twice here, guys. I just want everybody to know that I do expect people, oops, that should be a 0. I do expect people to be able to multiply matrices together. And sometimes people get exposed on this because it shows up here. And I know it's been a few weeks, but if you need to review matrix multiplication, given a choice between reviewing matrix multiplication or going back and studying integrals from calculus, work on matrix multiplication. That's what Math 250B is about, right? So everybody's got to be able to like square out a matrix like this. And in this case, it's not very hard to do this. Notice that the first column here on the second matrix is all zeros. So if you start doing these dot products, right, this first column is going to just be all zeros for sure. And actually, similarly on the bottom row, you see on the left matrix, the whole bottom row is 0. So if I calculate anything involving the bottom row, it's just going to be 0. So those are all going to be zeros. Okay. I did that very quickly because the dot products are almost nothing to do. There's so many zeros in this matrix that it just comes right out. What about the middle entry of this matrix here? Oh, that's 0 plus 0 plus 0. Okay, so that's 0. What about the top middle entry? 0 plus 0 plus 0 again. I'm getting a lot of zeros here. Okay. The upper right corner, what is that? 0 plus 64 plus 0. That is a 64 right there. Okay, and then on the right middle, I have 0 plus 0 plus 0 again. So that matrix is almost all zeros. There's just one number in it in the far upper right corner, which is 64. If I now take that and multiply by a minus lambda I one more time, right? In order to cube this thing. If I do that, so if I put 0, 0, 64, 0, 0, 0, 0, 0, 0, and I multiply that by 0, 8, 8, 0, 0, 8, and 0, 0, 0. This one is pretty much, there's not enough numbers here to get anything to happen. The bottom two rows are automatically 0 because they're already 0 here. And this is a 0 here. And if you just work out, there's actually no way to get that 64 to touch any of the 8s. So this is all zeros. In the super defective case, the cube of your a minus lambda I will always be all zeros. Actually, it's a nice property about this particular case. That makes your life easier in choosing W3 because, again, what are the rules over here? The rules are that W3 needs to survive 2 powers of the matrix. It needs to survive this matrix, but should not survive 3 powers of the matrix. Well, nothing is going to survive 3 powers of the matrix, right? If you take this matrix down here, all zeros, and multiply it by any vector, it's just going to zero out that vector. So can I get a proposal here? Does somebody want to suggest a W3 that might work for me? This is the hard part, just getting this W, in this case, W3, chosen in a way that will be helpful for us. Marcus?
0, 0, 1.
0, 0, 1, is that what you were going to say?
Yeah.
Yeah, notice that I know in class last week, I think every single one of these things, I always had 1, 0, 0 showing up as the choice. 1, 0, 0 doesn't work here. Because if you take this matrix here and multiply it by 1, 0, 0, it will get killed when you do the calculation. And you don't want that. You want your vector W3 to survive this matrix. So the key thing is to have some number in the third slot. What I'm trying to get at the point I'm trying to make here is you can't just always choose 1, 0, 0. And in fact, it'd be very likely that I might try and make a problem where you can't just choose 1, 0, 0 because we've done it so many times. So here's a good example where we can choose something else. 0, 0, 1. Okay, so that's W3. Or that's a choice of W3. I mean, you could also have picked 1, 1, 1. That would have also been fine. But I think it's easier here to just pick as many zeros as you can get away with while still making sure that that 64 does touch the non-zero entries of W3. Okay, so is everybody with me on this? Good enough? Okay, so then let's think about what W4 would be. W4, if I forget what W4 is, I go back to my diagram. It'll show me where I'm at. To get W4 from W3, I'm just going to multiply by a minus lambda I. So here is a minus lambda I. I'm going to multiply that. Let's just use a different color for a second. I'm just going to multiply this by 0, 0, 1 because that was what W3 was. I'm just going to calculate this out. Again, I've got to be able to do matrix multiplication in order to get the right answer here. That when I dot this out, 0 plus 0 plus 8 on the first row, and then 0 plus 0 plus 8 on the second row, and then 0, 0, and 0 on the third row. So I'm going to get 8, 8, 0. I'm going to get, for W4, I'm going to get 8, 8, and 0 for my 3 slots. Okay, so that's W4. Remember that although I get to choose W3, I have to then live with W4. Okay, don't take W4 as, oh, I'm gonna change it to 1, 1, 0. You can't do that. If you were playing with just eigenvectors and you just wanted to scale it up or scale it down, that would be okay. But here we cannot change these numbers, even with EROs or anything, right? We just have to live with those values, whatever they happen to be. Okay, then I need to figure out W5, right, guys? W5. How do we get W5? Evan?
Just multiply W3 by A minus lambda I squared.
Okay, exactly. If I want to get W5, there's actually two ways to get it. You can either start from W4 and just multiply one time by A minus 8I. But what I prefer to do is exactly what Evan suggested, which is I like to go back to W3 again. Everybody would probably agree W3 looks a little nicer than W4 does. I like to go back to W3 and just hit it with the square of A minus 8I, right? And here's the square of A minus 8I. If I multiply this, I don't have room here, do I? If I multiply that matrix, so I'll just recopy it really quickly. Here's A minus 8I squared. If I multiply that by W3, which is 0, 0, 1, then let's see what we get. What we get is 0 plus 0 plus 64, and then 0, 0, 0, and 0, 0, 0. By the way, this should not be 0, 0, 0. If you were to get 0, 0, 0 for any of the W's, something's wrong, right? They should never be all zeros. So this one is going to be now 64, 0, and 0. That's going to be the W5. Okay. Questions about that? Everybody following this okay? Right, so once we have that, guys, then we can write down, well, we can write down x3, but we can also write down x2 if we do this little cheap trick where we just say, I'm going to call W1, W4, and I'm going to let W2 and W5 also be the same. Now we are good to go. We can actually write down x2 of t and x3 of t in this moment. We are in good shape to be able to do that right here. Okay, so for x2, I'm going to have e to the 8t times, so W1, which is the same as W4, so that would be 8, 8, and 0, plus t times W2, which is the same as W5, 64, 0, and 0. So there's your x2 solution. Okay. And then finally, we have x3 here. This is e to the 8t. And this time we start with W3, which is 0, 0, and 1. And then we're going to go plus t times W4, which was 8, 8, and 0. And then plus t squared over 2 times 64, 0, and 0. And there is x3 of t. Okay, and I'll put boxes here. Make these easy to find for myself. That's the second and third solutions for our system. We've already got the first one way over here. We got this one a while ago, x1 of t from here. And once I've got all three of those, I can go to the final answer. And just to remind you, you don't need to recopy them all out again. You can just write for your final answer, as long as I can find all of your individual solutions, C1 times x1 of t plus C2 times x2 of t plus C3 times x3 of t. This would be the final answer. And you could just write that down and I would know pretty much what you were trying to say. You've already got your x1, x2, and x3, and you just have to feed them into that linear combination. That look okay? So there's a super defective linear system. You guys know on my additional videos section of the Canvas webpage, I have at least one example of all three scenarios. One of them might have been the same one I did in class already last Thursday, but for the most part, I tried to give you at least one example of each. I think on the homework for tonight, there's at least one example of each of the three defective scenarios as well. So there's plenty of practice on that. Through the homework and also on the tests, you're gonna see examples of those cases as well, so. Okay. Oh, by the way, did everybody notice that W5 is a multiple of your eigenvector? Never gonna be surprised by that, right? The W5 should be just a scalar multiple of whatever your eigenvector was. That's another little test to make sure things are looking good, okay? If you work this out and you feel like something's not quite right, okay, don't erase everything off your paper, right? Maybe use some scratch paper to check yourself if you feel like something is wrong. But there could be a lot of good stuff that I can give you partial credit for. And so it's better to keep it on there and let me go through and evaluate it a little bit. Tony?
So what you're saying is W5 is the same as this one right here?
It's not the same as. W5 is a scalar multiple of that will always be true. Yeah. It's whatever the last vector is on the diagram before you hit 0, that vector is always a legitimate eigenvector. So it should be, it doesn't have to be exactly the same as the eigenvector that you had here, but it should be a scalar multiple of it, or it should be in the span of the eigenspace. Let's just put it that way. Right. So that's a nice little way to kind of check yourself a little bit. Good enough? Okay, let's go on to another problem, and I am gonna jump around. That's okay, because I think that's probably how the test will go as well. So let's go to another problem here. So I'll go to number 2, and I'd like to do this problem. I would like to find the general solution. Okay, and I'm going to give you the problem right here. Y double prime plus 4y prime plus 4y equals the ln of x all divided by x e to the 2x. Okay. So this is the second problem. Now, I have to ask you right away, do you know, is this chapter 6? Is it chapter 7? Is it chapter 8? Or is it chapter 9? Lynn?
It's chapter B.
Sure looks like chapter 8 to me. It looks like this stuff right here. Okay, we have L of y equals F. The L in this case, the L here would be d squared plus 4d plus 4. Right, the d's just represent taking derivatives, right? So that's what you would have. So yeah, and this is the capital F over here on the right-hand side, the f of x. And so I might ask you to find the general solution here. So we have a 3-step process that we've learned. But let's just start talking about the first part of it here. The step 1. Step 1 is where we ignore the right-hand side for the time being. We don't worry about the big F. We just focus what's here on the left. And if I focus on what's here on the left, what do I need to write down first? R squared plus 4r plus 4. This is, what do we call this equation again? The complementary function is part of the solution. What is this equation called? Auxiliary equation. Yes, that's right. This is the auxiliary equation. And literally, guys, you're just turning derivatives into r's here. That's it. So you just turn all of the d's into r's, you get this thing here. This is just a quadratic, so we got to be able to factor that. And this one actually factors nicely. It's just going to be r plus 2 quantity squared. Okay. And so what are my roots going to be? Yeah.
-2 twice.
Right, -2 and -2. Just write it down twice here. And so I have a repeated root of the auxiliary equation. That doesn't bother me too much. It just means that when I write down this complementary function now, I'm going to be stacking an x, right? Remember the stacking of x's that goes on here? So you'll have a c1 e to the -2x. And then the second term is C2x, e to the negative 2x. We stack those x's in front of those two terms, okay? So this is step one. And even if you're not sure how to do the rest of the problem, do as much of it as you do know how to do, right? Because I can give you credit for each part of the problem as you go along. There could be some partial credit that we have. So this is the first part. Is everybody okay with that much? Okay, then we have to go to step two. And step two is where we have to find one particular solution. So I've still got it on my recap over here, how this is laying out. And according to step two, we have two methods. And so I'm curious, probably on the test, guys, I'm not going to tell you. I'm not going to say, oh, use annihilators or use variation of parameters. I'm probably going to leave it up to you to figure that out. So you need to know things like, well, I couldn't use variation of parameters unless it's second order. I can't use annihilators unless I know how to annihilate the function capital F of x, right? So those are, in the background, you have to know those things here. So looking at the situation we have here, does anybody see one of the methods maybe more favorable than the other one? Nathan? Okay, variation of parameters would be what I would choose. It's second order, right? We look at the differential equation, it's only second order. The other thing is this capital F, right, is not something that we have an annihilator for. I should have said this at the beginning. Of course, you're going to have the table of annihilators and integrals in your exam. So you'll be given that table. And you're going to see in that table, there's no logarithms in the table. There's nothing about annihilating anything with a logarithm. And there's also nothing about annihilating fractions. Okay. I'm going to just, don't write this down. I just want to play a quick game with you for a quick second. Suppose that this was, well, let's just do this. Suppose that the problem was this instead. Okay, don't change your notes, but I just want to play with this for a second. Would it be correct to say that I can annihilate that by using d squared plus 1 divided by d squared times d minus 2? Does that work that way? Yeah.
Oh, because if I remember correctly from the annihilator video, you have to multiply them, divide them.
This wouldn't even make sense. I wouldn't even know what it means to divide derivative operators, right? This would be exactly right, Liam. This is not something that would actually make any sense at all. If you start taking derivatives of a fraction like this, you're gonna have to use the quotient rule. And the quotient rule on something like this is just gonna make this thing even messier. And to imagine doing it 2 or 3 or more times, it's just going to get very unwieldy. To imagine annihilating this thing by taking various derivatives of it just seems crazy, right? I wouldn't even imagine doing that. But I have seen students try to write that down before, that kind of thing. So be cautious about that. You can't just look at each little part of it and figure out the annihilator piece by piece. Right? It should be laid out directly in your table. In that table, I only have like 9 things in that table. And I think you all have had a chance to use that table a little bit. So that should help you out. So even if you have a fraction and you say, oh yeah, each part of the fraction, I have something in the table for it. You don't actually have anything with a fraction in the table. So you can't use the table. This is important because this is a way that people get no credit on a 10-point problem. They see something that's supposed to be done with variation of parameters and they start trying to do annihilators on it. It's very hard to get partial credit for stuff like that. So this is a big deal. We got 2 options here. We got to get it right. We got to get the right option. So in this case, it's definitely going to be variation of parameters. In order to set myself up for that, I'm going to identify these 2 solutions here that we got in the first part as y1 and y2. And I just want to remind everybody that if Alex decided to call this one y1 and this one y2, he would be just fine, right? It doesn't matter which one is first and which one is second, but we should make a choice, right? And then when I go to step 2, I like to start with the Wronskian, because you see the U1 and U2 involves W. So the Wronskian is this determinant, as you guys remember. Give yourself enough room to write this out. Remember, this is not a matrix of numbers. What we do here is we lay out the functions into these columns. So the two functions y1 and y2, we put those right there on the first row. And now we have to take derivatives down this matrix until it becomes a square size. So we're going to get it into a square size matrix. So I'll pull down the -2, e to the -2t, is it -2x, I'm sorry. And then on the second column, I actually have to use the product rule. And the product rule is going to give me -2x e to the -2x plus e to the -2x. Just like so. It's a little 2 by 2 matrix here. And now I will use the simple formula for a 2 by 2 determinant. Upper left times lower right minus upper right times lower left. So that's e to the -2t, -2x, sorry, times -2x e to the -2x plus e to the -2x. And then we have to subtract, I don't have enough room here. Let me write this out a little bit better. So I have e to the -2x, and then I have -2x e to the -2x plus e to the -2x, and now plus upper right times lower left here, I have a factor of 2x, and I have two factors of e to the -2x, which actually gives me e to the -4x. Notice that I put a plus here. That's because it's really minus a negative. So it turns it back into a plus again. And guys, this last term here will actually cancel with this term as soon as I multiply it by e to the -2x. And the only term that survives is actually this e to the -2x times itself, which gives me e to the -4x. So a little bit of calculation there to get that part worked out. That's the Wronskian. Okay, great. So with that in mind, now I can try to start figuring out U1 and U2. Okay, so we have the formulas, they're still on the board here. Let's see if we can figure out U1 and U2 for this variation of parameters method. Okay, so U1 is negative the integral of y2 times f, all divided by w. Okay. And so let's put the pieces in here that we need. This is going to be minus the integral of y2, which was x e to the -2x. Capital F, which is the ln of x, divided by x e to the 2x. And then the Wronskian is also on the bottom. That's e to the -4x. All of this has a dx on the end of it. We just have to work out this integral. And it sure looks like the x's are going to cancel on the top and the bottom there. And actually, it's better than that. The exponentials, see e to the 2x and e to the -4x, actually combines into just e to the -2x, which is exactly what's on top. So the fraction completely cancels out. Right? Everything cancels completely. The only thing that survives this, guys, is the ln of x. And we have a minus sign. Don't forget the minus sign out in front. Just negative of the integral of the ln of x. And that one's actually going to be in your table. If you want to get a gold star or anything, you could actually work it out by using integration by parts. But really, there's no need to waste your time on that. I have it in the table. It turns out to be x ln of x minus x. Okay, so that's all going in place of that integral. Okay, so that's U1. I'll just remind you that because we're looking just for one particular solution here, there's no need to add a plus c on this antiderivative because we just need one particular solution. So this is perfectly good. Choose c to be 0, basically. Just makes things a little easier for you. So we're basically good to go with this U1 right here. Am I going too fast? Everybody with me? I wanted to do one of these because the only other time you saw a variation of parameters was when you watched me do a video. And I want to make sure that you guys are following. Okay, great. So that is U1. Now let's do U2. U2 does not have a minus sign on the integral, but we have the integral of y1, which was e to the negative 2x, times capital F again, which is the ln of x over x e to the 2x. And then my Wronskian is still e to the negative 4x again on the bottom. I'll feed that in. Okay. And again, the exponentials completely cancel out. This time we just have the integral of the ln of x over x. Okay. Now, guys, this one will not be in your table. Keep in mind, if you get to one of these integrals and you can't do it, and you're like, I don't see it in the table and I don't know how to do it, right? Please don't just punt on the whole problem completely, right? You probably have lots of partial credit worked up to that point, so don't just erase everything, right? If you get to some integral here that you can't do, honestly, if it was me on the test and I got to one of these integrals and I don't know how to get this integral figured out, I would probably be writing this down, writing this down, writing this down, and going on to another problem and coming back to it later. I would not get hung up on something that's probably only worth 1 point, maybe 2, right, at the most. It's not worth it to spend like 15 minutes trying to figure out why is this integral not coming out, right? Chances are the integral is not supposed to be that hard because I'm not going to be writing a test where the integrals are that hard. But if you get something where the integral is looking pretty intimidating, chances are something might be wrong somewhere. Maybe you just miscopied something or got the Wronskian wrong or something like that might have happened. It doesn't mean your exam is a total disaster, right? It just means, oh, maybe somewhere you made a simple little mistake that is turning something that was supposed to be really easy into something that now seems really hard, right? But it's no reason to panic, right? Because you have to know that I'm not basing partial credit just on is the final answer right or wrong. I'm going to be looking at, do they know the process? Did they use the right method? Are they, for the most part, competent with all the steps? And of course, I mean, even myself, right? I'll make sign mistakes from time to time. I'll miscopy stuff from time to time. Happens to everybody. Even seasoned mathematicians can do that. So try not to be too hard on yourself if something like this happens. Just don't panic. If you get to an integral that you don't know how to do, I would just set things down. Make sure that you've shown as much of the 250B stuff as you can on your paper, so I can give you as many points as possible. And then if you have time, of course, later you come back to it, right? And try to see what might have gone wrong. But in this case, this one is doable how? Evan. That's right. That's right. The if I just let u equal the ln of x, the derivative of that is just 1 over x. So you have u du sitting here. The antiderivative of that would be u squared, which would be the ln of x squared over 2, right? And again, we don't need a plus c on the end of that. Okay, perfect. So we have that much. Now, let's write down the particular solution, which we've still managed to keep on the board all this time somehow. So the y sub p of x, right? This is the step 2, conclusion of step 2. We have u1 times y1 plus u2 times y2. So u1 is negative of x ln x minus x. So negative of that quantity times y1, which was e to the negative 2x, and then plus u2, which is the ln of x quantity squared over 2, times y2, which is x e to the negative 2x. So here you go. I'd put a box around that one as well. That's the particular solution. So we've done step 1 and step 2 now. So far, so good? Okay, and then finally, for step 3, I don't need to see you write it all out again in longhand. If you just want to tell me that y of x is equal to y c of x plus y p of x, and put a nice box around that as well, I will take it that way. I'll take it in that form. So that becomes your your general solution for your problem. What do you think? Does that look okay? Question, Marcus?
Wait, so, when you have like the.
That comes up in the annihilator method.
Okay.
Yeah, in this method, that doesn't come up at all. Yeah, the constants, which are the C1 and C2 here, those constants are part of your answer. The only time you would actually solve for these constants would be when? Liam? If there were initial values, exactly. So if they gave us an initial value problem, we could actually solve for C1 and C2. You would only do that at the very end, after you've done steps 1, 2, and 3. You already have this general solution. Then if there was initial values given, like y of 0 or y prime of 0, things like that, you could use that to then go back and solve for the constants later. But that would happen at the end. Yeah, good question. Any other questions on this example? Far so good. Okay, let's go on to another example. Let's do number 3 here. Let's try this one. Let's again find the general solution. Okay, and so here's what I want to do. I want to do y with 4 derivatives on it, plus 13 with 2 derivatives on y, and then plus 36y. And this is going to equal the sine of 4x. Okay, let's take that as a good example. We're going to try to solve this one. Okay. Where does this fit into the material? Is this chapter 6, 7, 8, or 9? Looks like chapter 8 again to me as well. There's nothing about kernel and range. That would be chapter 6. There's nothing about eigenvalues and eigenvectors. That would be chapter 7. This is not a system of differential equations. That would have been chapter 9. This is just, again, an nth order linear differential equation. In this case, n is what? 4. Okay, 4th order differential equation. So let's try and go through this as well. What's my first step going to be? The auxiliary equation. Does anybody want to tell me what they think it is?
4
Okay.
plus 13r squared
Uh-huh.
plus 36r.
Actually, it's just
36.
it's just 36, right? There's no derivative on that term, right? And so this is going to then be equal to 0. Very good. So there's your auxiliary equation. We can just start by writing that down. And now here you have a situation where this is not a quadratic. And so it might be a little bit, might take a moment's pause as to like, how am I supposed to get the roots of that? Remember, there will be 4 roots. If I count repeats and complex numbers and so on, there has to be 4 roots. Does anybody have a suggestion how we could get roots out of this thing? Or how we could factor it at all? You know, if it was just this, the 13 and the 36 are really nice. Is there something I can do? You see it?
Group it with r squared plus 4.
R squared plus 4. Somebody want to help him? Jason?
R squared plus 9.
R squared plus 9, exactly. See, the trick is that 4 times 9 is 36, and 4 plus 9 is 13. And so this actually works out really nicely. If you were to FOIL that out right now, if you expanded this out, you would get r to the 4th plus 13r squared plus 36 is exactly that equation. And that's what you would see if you were playing with this one as well. It's just x plus 9 times x plus 4. Yeah, so it's totally the same type of thing. It's just been powered up a little bit. by the powers of r here. So this is one that I would expect people to be able to get, even though it's not a quadratic. Should be able to get these roots. And now each of these quadratics can itself be factored into the roots. Does anybody know what the roots of r squared plus 4 would be? Plus or minus 2i, right? Plus or minus 2i. If this was a minus 4, then it would have been plus or minus 2. Because of this plus, we have to go to the imaginary
I
number.
said 2i.
Oh, you did? Oh, I'm sorry. I just didn't hear you. Sorry. Okay, plus or minus 2i. And then how about the other roots of the other polynomial? Plus or minus 3i. Great. Okay, just making sure. Notice we have no repeats here. We have 2i, negative 2i, 3i, and negative 3i. So there's no stacking this time. There's no stacking of roots here, but I do have purely imaginary roots. And so I'd like to try to write down the form of the complementary function now based on those roots that we have so far. Does anybody want to give me a stab on the first term? Nathan?
C1 cosine 2x plus
Nice.
C2 sine 2x.
Okay, why don't I stop you there? Is everybody good so far? Question?
To be in that order of cosine first?
No.
Okay.
You could start with sine and then cosine. I generally do cosine first, but it doesn't matter. Yeah. Can I get somebody else to take it from there? Somebody else want to give me more of the terms here? Tony?
C3 cosine 3x
Nice.
and plus C4 sine 3x.
Super. So C3 cosine of 3x plus C4 times sine of 3x. That looks awesome. There's your complementary function, just like that. Perfect. Okay, so that's step one. Let's put a box around that so we can find it later if we need to come back to it. That's the first step, is getting the complementary function. Okay, so now let's get to step 2. And on step 2, we are going to look for one particular solution. Question, yes.
So you don't stack the x because nothing's repeated?
Correct. There's no repeated roots here, so I don't have to put any x's down there. But don't be surprised, guys, even in class, I did a 14th order differential equation. Don't be surprised if I give you a pretty big one at some point on the test. This one is only a 4th order equation, so we have 4 terms here. And there's no repeats, but this problem is going to be a little bit time consuming for a different reason, which is that, well, step 2, you'll see. The particular solution, we have 2 methods. Variation of parameters and annihilators. Which method do you suppose we're going to go with here? Annihilators, right? Yep, annihilators, exactly. And that's because, among other reasons, one reason is we only learned variation of parameters for 2nd order. So if this isn't 2nd order, we can't use that method. And annihilators, well, let's see, the only hang up with that is if we don't know how to annihilate the right-hand side. But look at the right-hand side of our problem here. Sine of 4x, that's going to be right in your annihilator table. I don't know if you have this one memorized off the top of your head, but in case you don't, I'm just going to tell you, it's just d squared plus 16. Okay. And so the way I like to think of this, guys, let's just remember here, these roots that we got in the first part of the process, I like to think of those as what I call the old roots. Those are the roots that came out of the auxiliary equation at the beginning. This annihilator is going to bring in some new roots. So if we once again change all of the d's to r's and solve this for the roots, what roots am I going to get here, by the way? Plus or minus 4i. Guys, if you're not seeing it, if you wake up with a headache on Tuesday morning and you're like, I can't figure this out, you can always go to the quadratic equation to get these roots, right? So negative b plus or minus the square root of b squared minus 4ac all over 2a. I realize I've been kind of writing these down quickly without showing a lot of work, but if you are struggling with getting the roots of a quadratic, you always have the quadratic formula to fall back. Now, these are what I like to call the new roots. Are these new roots in any way repeating the old roots?
No.
In this problem, they are not. The old roots are 2i and 3i plus or minus. Now we have plus or minus 4i. So these roots are entirely, they really are new. I just want to remind you guys that if any of the new roots happen to be the same as some of the old roots, which can happen, if that happens, then that X stacking business that you did when you were thinking about repeated roots would have to be implemented now. If these were repeated roots, we would, when we write down the particular solution in a minute, we would stack X's that corresponds to these being repeated roots. But here, these are not repeated roots. They do not repeat what's old, and they are not even repeated themselves. So there's really no stacking of anything going on in this problem. Okay, so what we can do now, guys, is write down the form of the particular solution that comes from those new roots. Okay, does anybody want to give it a stab? I've got all the usual suspects here. Anybody want to try it? Marcus, I haven't heard from you too much. Go ahead.
That's A cosine 4x. Sine 4x.
Okay, A times the cosine of 4x plus B times the sine of 4x. That looks really good. By the way, guys, can somebody tell me why do I not have any exponentials here? Like normally, don't we have like e to the, ax or whatever showing up? Why are there no exponentials on this example? Darren?
Because the roots are in like the have an imaginary in them.
The roots are imaginary with absolutely no real part to them at all. Like if this had been 2 plus or minus 2i, we would have had an e to the 2x in front of it. But this problem has no exponentials in it because all of the roots are pure, what we call purely imaginary, right? They have no real piece in front of the plus or minus. And so it's because of that that our solutions don't have any e's in them. So this problem has no exponentials anywhere. Yeah, this looks really good. Now, if you had called these constants C5 and C6, that would not be wrong. But I like to change to new letters here to remind myself that, hey, I can actually find the values of A and B. Unlike C1, C2, C3, and C4, which are going to show up in my final answer without having a solution, the A's and B's, and if there was any other letters here, right, these have values that we can find. Okay. Now, this is what I call the form of the particular solution. If the question says to just find the form of the particular solution, you would just write this down and you would be done with step 2. And you would just leave the A and the B sort of unsolved for. So that would be if I wanted to make a question where you didn't have to spend so much time solving for the constants. But if the question doesn't say that, if the question just says, find the general solution, then you should expect that you are actually supposed to find these constants. Okay? I do want to say that solving for these constants can be tedious. I can see right now I'm going to have to take 4 derivatives of that thing. Okay? It can be tedious. It's also probably not worth loads of points. So it's not the sort of thing that, just like with integrations, getting caught up with integrals, I wouldn't get caught up with this either, right? But in theory, it should be pretty doable. Now, 4 derivatives is quite a lot, but the good news is these are easy things to take derivatives of. That's why I basically decided to go ahead and ask this. So I'm going to go ahead. Is that all right? Can we take 5 minutes and try to find these 4 derivatives? Let's see if we can do it. The first derivative, right? The first derivative of y sub p would be negative 4a sine of 4x plus 4b cosine of 4x. There's the first derivative, right? And then we go to the second derivative. So the second derivative, I'm basically just using the chain rule to take these derivatives, and every single time I do it, there's a factor of 4 that gets pulled out. So negative 16a cosine of 4x, and then minus 16b sine of 4x. There's the second derivative. Okay, and then we go to the third derivative, the triple prime, y triple prime of p of x. All right, now we have to pull down another factor of 4, so we're going to get 64a sine of 4x, and then minus 64b cosine of 4x. And then finally, I have to do a fourth derivative. I guess I'll put it down here so that I can line it up with the other terms. The fourth derivative, again, I pull down a factor of 4, 256a times the cosine of 4x, and then plus 256b times the sine of 4x. Oh boy. Okay, so that's what the 4 derivatives are. And I'm going to now have to plug all those in to my differential equation. Okay. So what I have to do, guys, is I go back to the left side here, and I'm going to plug in the appropriate derivatives with the scalars in front of those terms. So I'm going to see if I can do the plugging in part right here. Okay, so plug in. So I'm going to be doing 4 derivatives of the particular solution, and then I'm going to add 13 times 2 derivatives of the particular solution, and then I'm going to add 36 times the particular solution. This is going to be the terms we have. And it's going to be a little bit of writing. I have to write down the 4th derivative, which is the one on the bottom there. I'll start with that. 256a times the cosine of 4x plus 256b times the sine of 4x. And I'm going to, if you don't mind, I'm going to stack the terms vertically. So then I'll have 13 times the second derivative. Let's get the second derivative written down. Are you getting tired of this, writing all this out? It is quite a lot. So then we have a negative 16a times the cosine of 4x, and then minus 16b times the sine of 4x. And then finally, we add 36 times the original y sub p, which is a cosine of 4x plus b sine of 4x. All of that. All of that. And what is this? This is all supposed to be equal. This is all supposed to be equal to whatever was on the right-hand side over here, sine of 4x. Oh, well, you know why I liked writing it like this? Because all the cosine stuff is kind of piled in the front, and all of the sine stuff is kind of piled in the back. So if I figure this out on the left, I'm going to actually figure out how many cosine of 4x's do I have, and then how many sine of 4x's do I have. I'm just kind of curious how many I have of each. What do I have here? I have 256. Does anybody have a calculator? 256 plus 36, and then minus 13 times 16. 13 times 16 is 208. So 256 minus 208. Oh God. 48. 48 plus another 36 is 84. 84a of the cosine of 4x's. And the beautiful thing is that there's exactly the same number of sine of, oh, this should be sine of 4x right here. Sorry, I made a typo there. But there's also 84b of those. And again, this expression has to match what was given over here. Is everybody with me? I'm perfectly happy to slow down if I need to. Again, this is totally just like high school algebra, basically, lining up the terms here. But the idea is that, you know, you match up apples for apples. On the left side, however many apples you have, that's how many apples you have on the right side. So I see on the right-hand side, I don't have any cosines. I don't have any cosines. So this must be 0. There cannot be any cosines on this expression. And on the right-hand side, I have only one sine of 4x. So the left-hand side has got to match that. There should only be one sine of 4x on the right side. And if you're good with that, then you see that A has to be 0, and you see that B has to be 1 over 84. Right. Okay, so does everybody see kind of how I did that? The math itself is kind of tedious, but I do want people to know the process. You're just taking derivatives of this particular solution, plugging in what's in the box here on the left side and matching it up with the right-hand side, just balancing the equation on both sides, right? So A is 0 and B is 1 over 84, and that means that now I can write down my particular solution is just going to be 1 over, so now I'm just going to put in 0 for A and 1 over 84 for B, right? So my answer is going to be 1 over 84 times the sine of 4x. Just like so. And now I'll put a box on this one. And now I'm ready to write down the final answer, step 3. Okay, so step 3 then, guys. Step 3 is just to write the final answer. And the final answer is going to be y of x equals, well, you can just do it the way we did before. Y sub c of x plus y sub p of x. Just put a box around that and I'll be good. We see the complementary function was here. Just not have to rewrite it again. And now we have the particular function with the b value plugged in. A was 0. So this is the only thing we have on the particular solution. It's looking pretty good. Hopefully that's looking pretty good to everybody. What do you all think? Questions on that? Okay, we need to do, so I've talked a little bit about some of the problems from chapters 8 and 9. I'm gonna go back a little bit and do a couple of other problems if you guys are good with that. So good. So let's do, oh, by the way, these 2 problems that we just did are on group work number 14. So I just did this group work that we never had time to do in class. I just did it right now with these 2 examples. So that was kind of part of my method to my madness, is go back and make up some of the group work. Let's do another problem here. So this is the 4th one we're doing tonight. Let's let capital A be the matrix 2, 0, 3, and then 0, -4, and 0, and -3, and 0, and 2. And I'm going to have 2 parts to this question, so we'll do the first part here. The first part is going to ask you, is A diagonalizable? So standard question, this is very similar to the one that was on the extra credit quiz. If so, if it is diagonalizable, I would like us to find S and D such that S inverse times A times S is equal to D. I'm going to do this as part A of this problem. I'm going to start with this. While I'm erasing, if you guys want to start thinking about how you want to approach this, that'd be great, and then we'll start writing it out. Remember, guys, diagonalizable is just another word for non-defective. It really comes down to whether the eigenvalues of this matrix pull their weight or not. So the first thing I need to do is figure out what? The eigenvalues, exactly. And so for that, the strategy is going to be to take the determinant of the matrix that we get when we subtract lambda off of the main diagonal up here. So I'm going to subtract lambda off of every entry of the diagonal. So 2 minus lambda, 0, and 3. And then the second row is 0, negative 4 minus lambda, and 0. And then we have negative 3 and 0 and 2 minus lambda. Okay. One thing that has been a little bit concerning to me recently, so many of these matrices are set up with a lot of zeros in them that I've been noticing some people are a little rusty on how to figure out these determinants. We don't really want to use the arrow method here because the arrow method is gonna, you know, even the very first diagonal is gonna already have like a lambda cubed that's gonna be a mess of a term that has to be simplified with everything else. The arrow method will not leave us with a nice form to get the lambda values. So a better method is to use cofactor expansion. A lot of times it's better. There's at least one homework problem for tonight where the cofactor expansion, there really is not a good row or column to use. And you just have to suck it up and just deal with it. Just cofactor expand something and just deal with the thing. But remember, guys, when you do cofactor expansion, in theory, you are expanding all the way across a row or all the way down a column. I see a lot of people that are just like finding one right? You guys remember, right? The determinant of A, it's according to the cofactor expansion method, if I just used row 1, for example, it would be this. A11 times C11 plus A12 times C12 plus A13 times C13. But what a lot of students have been doing recently is they've just been doing this only. They've just been writing out one entry times one minor and stopping. And that's fine if there's only one non-zero entry in the row or column that they've chosen. But like here, if I was going to expand row 1, I would not just have one term. It would not just be 2 minus lambda times this. It would be 2 minus lambda times this, and then minus 0, and then plus 3 times this one, you see. So just be careful not to shortchange the cofactor expansion. Now, if you choose a good row or column, maybe you're right. Maybe there is only one term that you have to work on. Does anybody see a good row or column here? Somebody besides same suspects? Angelo, do you want to give me an idea? The top row would certainly be, any row or column is fine. I probably would not pick that row though, because I only have 1 0 there. Is there a better choice, Gwendolyn?
2.
Yeah, how about row 2, right? Row 2 is going to be much nicer because there's 2 out of 3 zeros here, right? So if you did row 2, you would have A21, C21 plus A22, C22 plus A23, C23. But these numbers are both 0, you see. And so you only have to do one term then, right? So this can make or break, right? This can make or break getting these lambdas is really picking a good choice of a row or a column. The more zeros you have in that row or column, the better. Okay, so I'm going to use row 2. I'm going to expand row 2 right now. And if I do that, let's also remember we have our plus minus thing. In row 2, I only have this middle entry, and there's going to be no sign change on that middle position. So I'm just going to write down the negative 4 minus lambda times, okay, now I have to cross off this row and column. Let's use some big brackets now to do the 2 by 2 minor. that is still with us. So I have 2 minus lambda, which is twice, right? AD minus BC, the 3 times -3 is -9, and we subtract that, it becomes +9. Okay? Now, just a quick reminder, it's best not to multiply this all the way out. If you multiply this all the way out, you're just gonna end up with a cubic equation, and you're gonna be wishing that you could find the roots more easily. So it's better to keep it nicely factored. So I'm gonna leave the -4 minus lambda there. And I'm just gonna go into these brackets now and go ahead and FOIL it out. Inside the brackets, I'm only gonna get a quadratic equation, so I'm perfectly comfortable with that, just FOILing out the part in the brackets. So I'll have a lambda squared, and then the outers and inners, -2 lambda, -2 lambda, that's -4 lambda. Right, and then I have a +4 and a +9, which can be combined into +13. If I did the math right on that, this is what we should have. As always, with these characteristic equations, we need to set those equal to 0. Set that one equal to 0 now. Awesome, and let's get our lambda value. So here we have lambda equals -4 from this first part. And then on the second part, I'm actually gonna have to use the quadratic formula because this one does not factor nicely, but it does have 2 roots if I'm willing to just persist with the quadratic formula. So the quadratic formula for lambda would be what? 4 plus or minus the square root of 16, so 4 squared, which is 16, minus 4ac. 13 times 4 is 52, I think. And then that's all over 2. All over 2, like so. All right, so let's just recopy the lambda values here. We have -4, and then the 2 other roots are going to be 2 plus or minus. Now let's see. This is the radical of -36. What's the square root of -36? 6i, right? 6i, which then gets divided by 2. Don't forget that the 2 is under the whole thing. So 6i divided by 2 is just 3i. We end up with 2 plus or minus 3i. These are the lambdas for this problem. And so then the question I have to ask you is, are we able to answer the question yet? Do we know, based on the eigenvalues here, whether this matrix will be diagonalizable or not?
Yeah.
We do know, and what is the answer?
Yes.
And the answer is yes, this will be diagonalizable. That's because there are no repeats. If there are repeats, does that mean that it's defective? Not necessarily, right? Even if there was repeats, there would be a chance that it could still be diagonalizable. It would just come down to whether the eigenvalues that repeated pulled their weight or not. But in the case when there's no repeats, like here, there's no repeats, then we already know, even before we take a breath, we already know that this is diagonalizable. So the answer to A is a yes. And it asks us to find S and D such that S inverse AS equals D. We actually know how to do that. Remember that the D matrix is just the diagonal matrix with these lambdas on that main diagonal, right? And the S matrix is just the matrix with the eigenvectors lined up into the columns of it, right? So we actually have to find the eigenvectors here. Let's just take a minute and practice that again. So for lambda equals -4, we have to do a null space here. Okay, so this is a null space. And essentially what I do is I take the matrix A and I subtract the lambda from the main diagonal. Well, subtracting -4 from the main diagonal is like adding 4. So I add 4 to the main diagonal, I'll get 6, 0, and 3. And then I'll get 0, 0, and 0. And then I'll get -3, 0, and 6. So I have just added 4 to the main diagonal of the matrix. As I've reminded you many times, I'll say it again tonight as well, this matrix cannot be invertible. there must be a row of zeros either already there, or if I did EROs, we would get a row of zeros. I'm gonna go ahead and cross off any row of zeros that I see. Okay, so there you go. We can just do that much. And I'm gonna do a quick ERO here. I'm gonna take the first row and divide it by 6, if you don't mind, just to get a 1 in that upper left corner. The row of all zeros, I'll go ahead and throw that on the bottom. Can permute it to the bottom if we want. And now I'm gonna do this kind of quickly in my head, guys. I'm gonna take 3 times this new first row that I have and add it to the bottom row here because I want to change this -3 to a 0. So I'll end up getting 0 and 0, and what did I say I'm doing? I'm multiplying this by 3 and adding it to this. So 3 halves plus 6, 15 halves. You know, honestly, guys, it really doesn't matter what it is. It's not gonna matter because what's gonna happen now when you get this into sort of a row echelon form is that, well, z is 0 and x is 0. You can see that the x and the z are both going to be 0. The free variable is y. The free variable is y, so I'll just label it as t. And if we bust out our variable here, I think I'll do it down here. We bust out our t, we're going to get the eigenvector 0, 1, and 0. So there you have it. That would be your first eigenpair for this matrix. Good enough? Let me know if I'm going too fast here. We have another eigenvalue. Let's go and work on that one. Lambda equals 2 plus 3i. Let's see if we can figure out what's going on with that eigenvalue. Again, I'm going to start by writing out a null space for our eigenvectors. We're going to need to use this null space. So I'm going to subtract 2 plus 3i from the main diagonal of A. So I take the matrix A, and I'm going to subtract from the main diagonal, I'm going to subtract 2 plus 3i. So that's going to give me -3i, 0, and 3. And then 0 and -6 minus 3i and 0. And then in the bottom row, I have a -3 and then a 0. And then again, I'm subtracting 2 plus 3i from the main diagonal. So this becomes a -3i. Okay. I wanted to do a 3 by 3 example that has imaginary numbers in it. We haven't seen a lot of those, but here we have one. Here we have it. Now we know, even though it may not be as obvious this time, we actually know that these rows have to get, well, at least one of them has to get zeroed out, right? I actually can see that if I multiplied the bottom row through by I would get the top row. The first row and third row are actually multiples of each other. It may be a little bit of a stretch to just eyeball it, but it's not too hard to see that. So I'm just going to get rid of the third row, knowing that it really is a multiple of the first row. Okay, that's a pretty safe thing to do. And I'm going to keep the first 2 rows with my pivots just like that. Now, you ready for a little bit of shenanigans here? I'm going to try to get my vector without breaking a sweat. If I read off on the second row here, what's the second row say? The second row says 0 times x and -6 minus 3i times y plus 0 times z. Do I need to write that down? 0 times x plus -6 minus 3i times y plus 0 times z. And if we're doing a null space, that means we're setting things equal to 0. But what does that allow you to conclude? Y is 0. You see, this x term is gone. This term is gone. The only thing that survives is this middle term, some number times y equals 0. That tells me that y is 0. So y is equal to 0. Okay, so far so good. Now, what about the x and the z? Well, that's obviously going to be related to the first row. That's where I see the coefficients for the x and the z, and there is no y influence at all on the top row of the matrix, okay? You guys remember my little A-B trick? Now I know that on that A-B trick, I was always doing 2x2 matrices. Probably remember there's only two numbers. I have A here and B here. Then I can make my vector by swapping them and doing a sign change. You haven't seen me do it so often on a 3x3 matrix, but you know what, guys? You can do it here. Just with x and z. Basically, y is already taken care of. I'm just looking at the x and the z, and this is my A and my B on that A-B trick, and I'm just gonna kind of ignore the middle slot. I mean, like not even think about it. It's not really there. If you don't like this, of course, you can set up a free variable for z and then solve for x. But notice when you're solving for x, if you were going to do that, if you wanted to solve for x in this equation, you're going to have to divide by a complex number. And dividing by I is not so terrible, but what if it was, I don't know, negative 3i plus 5? And so then your x would be like, I don't know, negative 3t divided by 3i plus 5. This is pretty nasty to be writing it down. It wouldn't be wrong, but you know, you start wanting to divide by complex numbers, you really do need to go to the appendix of the book and figure out, well, how do you actually do that? It's just a hassle. It's kind of messy and it's not really worth it. So it's just so much nicer to just do my little A-B trick here. And I'm just gonna do that. I'm just gonna do that. So I'm gonna put x to be the negative of the b. And the z is just gonna be whatever the a was. So we can just do that. Let's actually start writing the vector down, right? So my eigenvector y was 0, right? And what about x and z? I'm just gonna take these two numbers, I'm gonna swap them, and then I'm gonna do a sign change on one of them. It doesn't matter which one you do the sign change on. So in this case, I put the sign change on the 3, but you could have put it on the negative 3i if you preferred as well. This would be a good answer. Okay, so this is the eigenvector for that eigenvalue. Everybody with me? So I'm doing this little A-B trick, even though it's a 3x3 matrix, because one of the three variables is kind of out of the picture. And so I can treat this almost like it's just a 2x2 problem. Marcus.
Should this be x equals negative 3?
Oh, yes, I did not mean to, I'm just making sure everybody's paying attention here. That I should not have been there. I'm so sorry. Yeah, I got it right down here. Exactly. Okay, so now can I stand on this chair safely?
Probably not.
You guys don't think I can do it? I just climbed a 20,000 foot mountain. You don't think I can stand on this chair? I'm gonna try to stand here. I'm balancing really well because I just don't want to erase anything. Can we write down the other eigenpair just from? I wish I was a foot taller, then I wouldn't have to worry about this. Can we write down the other eigenvector immediately from this?
Yeah.
Do you remember how to do that? We just have to conjugate that eigenvector. I'm going to try not to get too excited while I'm standing up here. I just take that vector and I change only the I parts. So there you have it, right? That's going to be it. And now I'm going to step down safely. Yay! I made it. Right. So that way I have it all on one board. So here's this eigenpair, right? And then we have this eigenvector with this eigenvalue. So I've got everything I need, right? So we should be able, let's see if we can write it down now. What is the S and the D? So again, guys, to write down S here, let me go ahead and get my computer set up for that. To write down what the S is, all I have to do is lay my eigenvectors into the columns. It doesn't matter what order I do it in. So I can just put 0, 0, 1, 0 here. And then my second eigenvector was negative 3, 0, and negative 3i. And then my third eigenvector was negative 3, 0, and 3i. So this would be S. And the only thing we have to be careful with D now is that we put the eigenvalues along the diagonal in the same order that lines up with the eigenvectors. So the first column corresponded to negative 4. The second column corresponded to 2 plus 3i. And the third column corresponded to 2 minus 3i. And that was it. That's it. Yeah, go ahead.
Back at that null space, if you crossed out the first row or something and then change around, did you get the vector where x equals like negative 3?
So if we crossed off this row instead, and then we tried to do the AB trick here, we would have gotten something like 3i and negative 3, right?
Yeah.
And you're like, well, wait, that's not the same as this one. But you know what it is? It's a scalar multiple of this one.
Okay.
If you take this one and multiply it by I, you'll get this one. And one thing we've learned for sure about eigenvectors is that a scalar multiple of a good eigenvector is just another eigenvector. And it's just as good as the first one. Yeah, so you can certainly get away with that. Other questions on this? Okay, there's a part B I want to do here, guys. I know it's after 6. I'm probably going to keep talking for a little while longer. I haven't even gotten to quite everything yet, but it's okay. If you need to leave, it's totally fine. I'm still recording, and if you want to pick this up at another time, you certainly can. But I think I'm going to keep going for a few more minutes. I have a really good. This is a great turnout, by the way. Like almost half the class is here. It's awesome. The second part of this question is just simply going to be find the solution to x prime equals ax. So we're going to do x prime equals ax. Come back over here. And then I'm gonna probably the two other things I'm gonna do, just in case anybody's wondering what else I'm gonna do tonight. I'm probably gonna do one problem about kernel and range. I'm also probably going to do one theoretical problem about eigenvalues and eigenvectors. I haven't done either of those things. And then I'll probably save anything else for tomorrow. I'm gonna do a review again tomorrow as well. But let's do this first because we have everything on the board that we need to try to solve this system. Okay, so remember, if I give you a linear system and I ask you to solve it, first thing you need to do is find the eigenpairs. This matrix was diagonalizable. It was not defective, so we don't need to use the W's that we learned about on Thursday. We can actually just start writing down the solutions here. So for part B, the solution for part B, I can make one solution, which I'll call x1 of t, which is just e to the negative 4t times 0, 1, 0. I can literally just write that down. We've already done the work. We've already done the work of finding the eigenvalue, eigenvector pair, and we're just writing down the solution in that form now. Okay? To get the other solutions, remember here, we have complex numbers. And so when you have complex numbers, I just want to remind you, this is not a 23, this is going to be a 2 and a 3 together. I'm going to combine, we're going to get two solutions kind of at one time by writing down e to the power of 2 plus 3i times t, and then the corresponding eigenvector, which was negative 3, 0, and negative 3i. So I'm going to go ahead and write that there. You guys remember what it is we have to use to... These are not real solutions here. This is not real. We have I in it, but do we remember how to get rid of the I? Audrey? Yeah, we take out the e to the 2t, and then we use Euler's formula on the imaginary part of this, right? So I see e to the I with a 3t in front of it. So this is going to be cosine of 3t plus I times the sine of 3t. Okay, so that's how we sort of clean up the first part of it with the exponential. Okay, so remember, whenever you have e to the I theta, you can break it into sines and cosines. This is what we're showing here again. And then the other thing we're going to want to do is take the vector part and split. We also want to split it up into a real part and an imaginary part. So the part that does not have I on it, which is -3, 0, and 0, right? And then I'm going to do plus I times the part that does have I on it, which would be 0 and 0 and -3. It's kind of like busting out the variables, but the I really technically isn't a variable, okay? But it's the same idea. You kind of split this vector off into the real piece and the imaginary piece, like so. Okay, and then what do we do next? Liam?
We just add the two, the two together.
I'm not ready to do that yet. I still have the I in the answer here, Julia, do you remember? This is where we have to do the FLOI, that FLOI thing where we sort of, well, you FOIL this out, but you're gonna do it into two parts. So I'm gonna go ahead and remind you here, the e to the 2t stays in front all by itself. And I'm going to FLOI this out, okay? So that means I'm gonna do the first, which is cosine of 3t times -300. And then it would be, so that's the first, F. And then the L part, which is the last part of the FOIL, that would be I sine 3t times I 0, 0, -3. But what is I times I? -1, right? So there's going to turn it into a minus here. We're going to end up with a minus. There'll be a sine of 3t times this vector right here, which is 0, 0, and -3. I think I mentioned in class that it is possible to sort of memorize what goes where here. Like, you know, which part of the vector goes with sines and cosines and where you have pluses and minuses. It's not worth memorizing it. It's better to just FLOI it out every time, right? So that's the first and the last. And then for the outers and inners, we'll have an I that gets factored into the front. So here I'm going to do outers and inners. I hopefully have enough room here. I think I can make this work. For the outer term, I'm going to have cosine of 3t times 0, 0, -3. And then plus the inner term is sine of 3t times -3, 0, and 0. So it'd be like so. Let you guys copy that down, make sure I did it correctly. Obviously, you know, you've got some well, actually, you don't really. I was going to say there's like a double negative here. There's no need to clean that up. You can just leave things with the signs the way they are. Is everybody able to read that okay? Yeah, and now I'm ready to extract the two real solutions. Remember that the two solutions, I'm going to call them x2 of t and x3 of t. The x2 is going to come from the first and last part of the FOIL, and then the x3 is going to come from the outers and inners part of the FOIL. So we have two parts here. Let's just write them down. For the x2 part, we literally just grab everything here in the front and make a solution out of that. So it would look like e to the 2t times, and then we have the vector with cosine of 3t times -300, right? And then minus the sine of 3t times the vector 0, 0, and -3, just like so. So there's x2. And then for x3, we do the same thing. We still have to grab the e to the 2t, but now we're going to grab the outers and inners part without the I. Guys, one way to know that your answer is at least reasonable is you should not have any I in your answers. Right? You should end up getting rid of all of that. So here we will have cosine of 3t times 0, 0, -3 plus the sine of 3t times the vector -3, 0, and 0. Just like so. That's x3. So let's see, we wrote down x1 right here. That was originally the first one we had. Yeah, and now we've got two more solutions here. I'm gonna go ahead and put boxes on these. We have x1, x2, and x3 with boxes around everything, right? And so now we can write down the final general solution, which, as you know, guys, x of t is c1 times x1 of t plus c2 times x2 of t plus c3 times x3 of t. This would be it. This would be the answer. Look okay? Any questions on that? This is a nice problem. It's reviewed diagonalization, finding the eigenvectors, writing down the solutions to a Floyd system as well. Okay. Okay, so I want to do two more problems. One of them is going to be a theoretical problem about eigenvalues and eigenvectors, and then the second one is going to be a big whole thing on kernel and range, and one-to-one onto all that good stuff from chapter 6. Let's do, what number am I on, by the way? 5? Number 5?
Yeah.
Okay, perfect. So I'm going to give you this problem. So let's let A, which is n by n, be a matrix with A squared minus 7A plus 8 times the identity equal to the 0 matrix. Okay, so I'm going to make an equation here. And then I'm going to say, let's let lambda be an eigenvalue of A. And then I'm going to ask you to prove just a couple more questions here, guys. I'm going to prove, I would like you to prove that lambda squared minus 7 lambda plus 8 is equal to 0. Now, I don't have to use this particular, there's nothing special about the 7 or the 8 or anything like that. I could make any equation I want. This is a really interesting fact, that any equation that a matrix satisfies is also satisfied by any of its eigenvalues. This is actually a theorem that you would, definitely be discussing in more detail in a theoretical linear algebra class, but this is at the level that we can handle it. And I would not hesitate to ask you this kind of problem on the test. So given an equation that the matrix satisfies, show that your eigenvalue will satisfy the same equation. Does anybody have an idea what kind of a starting point I might want to think about for this? I know you know. Hold on a second. Julia? If I don't know anything else, and if I'm running out of time, or I just need to throw something down to show that I know something about theoretical problems dealing with eigenvalues and eigenvectors, if there was one thing you would ever want to write down, it would be this. Guys, it is the most important equation in chapter 7, and I've talked about it so many times. So this would be given, the V is an eigenvector, which is not 0. I just want to emphasize that here as well. But this is it, right? This equation is really important, but we haven't seen it very much tonight. That's because it's generally going to end up in the background. When you're doing eigenspaces, all this stuff over here, these calculations, you don't actually see that equation kind of playing a major role. But yet, this is really where the theory of eigenvalues originates from. It's why it's important. And so I do want students coming out of Math 250B to sort of have this in the front of their mind a little bit when they're thinking about eigenvalues. So yeah, this would be a great starting point. Okay, now, it's a starting point, but I don't know where to go from there. Does anybody have a suggestion here, Audrey? Okay, so we could take this equation up here. You notice in the black question, the black writing, the vector v is never mentioned. But now we have introduced the eigenvector as part of this starting point that we've written down. So it's actually a really good idea. I'm just going to make a note of that because I think you're absolutely right. This is going to be helpful. That if we took a squared minus 7a plus 8 times the identity and we applied it to v, it should be the same as if we took the zero matrix and applied it to v. So we can do that. We can take the given equation here, which I'm underlining in blue, and we can just apply it on both sides with v. And I like doing that. By the way, if I take an all zero matrix and I multiply it by a vector, what would I end up getting? All zeros, right? Absolutely. So on the right-hand side, I can think of this as just being zero for sure. Okay, so that's certainly going to be zero. And on the left-hand side, I can distribute this. This part applied to v, this part applied to v, and this part applied to v. Let's just write that down. So I would have a squared v minus 7ab plus 8v. Notice that the I has vanished now because identity, of course, is like multiplying by 1. So I times v is just v here. So this is what we would have. Okay, so we distributed that thing out. Looking pretty good to me so far. Any suggestions where we go from there? So far, you guys are doing great. Yeah, go ahead, Audrey.
So for a squared, substitute for.
Okay, I have a question. I want to see. You're right. You're right. But before I go any further, I want to show you what lots of students like to do. Lots of students see AV equals lambda. Don't write this down. Just watch for a second. Lots of students will start with that and they'll say, oh, I want to have a squared. I'm just going to square both sides. Is that okay? I don't think so. I don't know the last time that I ever took a vector and squared it, right? That's really what you're doing right here. It's like, could I take this thing here and square it? What would that even mean, right? It's multiplying the vector by itself. No, it doesn't make sense to square a vector. So I will see people trying to do this on a problem like this, but you guys, now that you're here and you're on your A game, paying attention, you're not going to do that, are you? Instead, the right thing to do is exactly what Audrey was suggesting. Now this part, we can write it down. I'm just going to make a little side note again, which is we're supposed to figure out what a squared v is. I mean, I want to kind of work on this first term here. And that is just a times v. If I lay it out, it would just be a times v. And I think what you were suggesting, if I'm understanding correctly, Audrey, is to just kind of do this. Just kind of think about the AV part. Say, oh, well, I can feed in lambda v for that. So the AV turns into, that's perfectly legit, right? AV can be replaced with lambda v. And now lambda is just a number. So I don't have any problem with just putting it out in front. It's a scalar, right? Just factor it into the front. And there you go. Now you have the lambda out of the way and you have another AV you can work on. And that other AV also turns into lambda v. You see? And now what you really have here, guys, is just 2 lambdas being applied to v. Lambda squared. It's perfectly okay to square lambda. I don't mind doing that. It's also okay to square a. What's not okay, what I do not ever want to see is something like that. We do not square a vector. That just doesn't make sense. Okay. So good observations here. Really helpful to make sure our notation is making sense. But guys, that now allows me with this with this little note, I can come back over here now, right? And I can say, okay, a squared v, I just worked out that that's just lambda squared v. So let's come back over here. A squared v, right? A squared v is just lambda squared v. And then what do I have after that? I have minus 7 times, oh, here's AV again. What am I going to do with that? Lambda v, right? So change that to lambda v as well, right? And then we have plus 8v. And this is all still going to be equal to 0. Nice. Okay, that's basically looking good. And so from there, oh, I'm getting close. I'm getting close. Does anybody see anything I can do algebra-wise with this bottom line here? I know I kind of squeezed it in there. Any algebra that looks favorable for me?
Nathan, can you factor out the V?
Yeah, I would factor out the v, absolutely. So every single term has a v on it. Is that what you were gonna say?
Yeah.
Yeah, factor out the v. I'm gonna come over here to the left if you guys don't mind. Just gonna factor the v out on the right side. Oh, I like this problem. Right, and I can change this polynomial 5,000 times. It doesn't change how the actual math is going to work. So I literally just picked these numbers right now in my head. Doesn't make any difference. So there you go. What do I have? I have v. By the way, v is not 0. But somehow, after I scalar multiply it by this scalar in front, it has become 0. Well, what does that tell you about your scalar? Your scalar must be equal to 0, right? Your scalar must be, this thing in parentheses has to be, this one's not 0. You're multiplying two things together and you're getting 0. If this one's not 0, then my friends, the only thing you could conclude is that this one is 0. That is exactly right. That's the conclusion. That's it. Right? But the driving calculation is really right here, right? If any of you need any extra practice on these theoretical eigenvalue, eigenvector problems, please go back and you did some homework on this. Might not be the worst thing in the world to spend 10-15 minutes reviewing a couple of the problems from a few assignments ago where you were practicing these theoretical problems on eigenvalues. If you need it, if you think it would be helpful. Yeah, Mark?
So part of the theorem may be equal to lambda v is that v is not equal to 0.
Yeah. An eigenvector has to be not 0. Yeah, that's exactly right. Okay. All right, I know you guys have been hanging in there for me. I'm gonna do one last problem about kernel and range, which we haven't talked about at all tonight, and then we'll call it a day. Unless there's any questions here. Y'all okay with this? This is awesome. You guys are getting, I think, a really good overview of some things here. So let's do one more example. This is number 6. And what am I gonna do? I'm gonna make up a problem on the fly. So I'm not gonna use the one that was exactly on the quiz, but I'll make up my own example here. I'm going to define t to go from M2 of R. It's going to be mapping over to P 4 of R via, and so let's do one here. Let's take T of, this is a 2 by 2 matrix, right? So I'm going to plug in A, B, C, and D like that. And what I'm going to ask on this one then is going to be, this is going to be equal to A plus B plus C plus B plus C times X squared plus B plus C plus D X cubed plus B X to the 4th. Sorry, I kind of almost ran out of room there. Is that readable? Can you guys all read that okay?
Yeah.
All right, so here's my question. I would like to know, I would like to find bases for the kernel of T and the range of t. Okay, and I would like to decide if t is 1-to-1 onto both or neither. This will basically take care of the whole chapter 6. We just do this one problem. Okay. I want to start by mentioning a major mistake that came up on the extra credit quiz and make sure that we don't make it again. The kernel of t is a subspace of V, and the range of t is a subspace of W. So that means that when I'm writing down things that are in the kernel of t, they should look like 2x2 matrices. And when I write down things that are in the range of t, they should look like polynomials, the degree 4 or less polynomials, right? Very often what happens is that you get caught up in the calculations. It happens to me many times also. You get caught up in the calculations and you start writing down slots. And everything looks like a slot. And so you'll have somebody writing down 4 slots for the kernel. And I'm going to look at that and say, no, it's not it needs to be a 2x2 matrix, right? And if I'm writing down stuff for the range of t, it's very easy to think of it as 5 slots, but it really should be a polynomial that we're writing down. Okay, so just to be a little careful about that. So do you guys remember how to find the kernel of t? I know this goes back a ways. Angelo? Okay, null space is a great answer if the transformation is going from Rn to Rm, and if there's a matrix A involved, then the null space of A would literally be the kernel of T, and that would be right. In this case, we may end up looking at we may eventually get to a matrix where we are finding its null space, but at this moment, I don't see a matrix over here that's actually creating the transformation. So I would probably not address it as a null space quite yet. Marcus?
You just said the right side equate.
That's exactly right. So for the kernel of t, excellent. Yes, we are just going to set t of a, b, c, d. We're going to set that equal to 0. This is how you find the kernel. Now, when I say 0 over here, this is not the number 0. This is the 0 vector of W. So when I write 0 there, I really should be thinking of it as 0 plus 0x plus 0x squared plus 0x cubed plus 0x to the 4th. Just to be clear, what is that 0? It's literally the 0 polynomial that we're talking about. So we're basically going to set this thing here, my friends, equal to this thing here. And you're just going to match up the corresponding terms. The constant terms have to match. The x terms have to match. The x squared terms have to match, and so on. So if I write that out, I'm going to create some equations here. A plus b plus c, that equals 0, right? And then b plus c, that should equal 0. And then b plus c plus d, that should equal 0. And finally, b, right, should equal 0. Okay, and here is where you could look at this and say, well, there is a null space here. So somebody was saying originally, well, we're going to find a null space. You're right, but not until we actually get to this matrix. I'm going to go ahead and write out the augmented matrix for this little linear system. So the first equation goes in as the first row here. And then the second equation goes in as the second row. And then the third row is looking like that. And then the fourth row is going to look like that. So you actually do get a matrix where you're finding the null space. But this isn't the first thought that comes into my head when somebody says, how do you find the kernel of t? My answer is usually set t of v equal to 0. Eventually, that might lead you to having to solve a system that does resemble calculating a null space, but this is coming a little bit later in the process. Right. Just because it's getting late, I think I'm going to, sorry, go ahead.
Oh, sorry.
It's fine.
Just in general, I don't know how to say this, but when there's a problem kind of like this, like it says, you know, it's B and W, and it says it's defined by.
Uh-huh.
Is the dimension of W, for example, like the thing in the initial smaller version, or is it based on
It's-
the description?
It's this big thing up here.
Okay, so don't like,
Don't go into the weeds of what the transformation is doing.
okay,
You just have to look, what is the universe that is the inputs and what is the universe that is the outputs? That's your V and your W. The dimensions are totally based on
For
that
like
alone.
comparing, okay, so it can't be.
Yeah, exactly. If you're trying to use the dimension theorem to compare the dimension of the kernel, the dimension of the range, and the dimension of V, you got to be using what's on the surface level up at the top of the problem. Great point. Yes, Evan.
On an exam, would you be okay if we just jump straight to that matrix, like with a null space, or do you want us to set up those equations? And
I could be, see, if, here's usually my rule of thumb on grading. If I feel like I could have done that in my head myself, I'm usually okay if somebody else does that also. What bothers me is when there's not enough work being shown and I'm looking at something like, I don't see how you could get this just in your head, then I get nervous about it. This one, I think you could, like I could see A plus B, C turns into this row. And B plus C turns into the second row and so on. That would probably be okay with me. Now, just to save a little time here, guys, because I know I've been going for a while. I'm gonna not do EROs here. I'm just gonna look at the system. Can you guys all see that since B is 0, then so is C? And since B and C are 0, so is D, and so is A. They're all 0. Okay, so just I'll save a little bit of a hassle with that. A, B, C, and D, they're all equal to 0. I'm just gonna kind of just jump to that point. And so what does that tell you about the kernel? It is just 0. Now, are you gonna write 0? Let's write what the kernel vectors should look like. They should look like 2 by 2 matrices. That's a big deal for me. I want people to write the vectors in the right notation. So this would be a 2 by 2 0 matrix because it lives in this universe, right? The kernel of T is inside of this universe. So I would want to see it written as a 2 by 2 matrix. Now, because of that, by the way, this is just the trivial space. So there isn't really a basis for it. I don't know if I really haven't mentioned this a whole lot, but if you have a trivial vector space that only has the 0 vector in it, there's no like basis for that. The dimension is just 0. And so there, I would just say there's no basis. Right? You could just say it that way. There's no basis. The dimension of it is 0. Let's just write that down. We might find that helpful later. So the dimension of the kernel should be just 0 based on what we've said so far. Okay. So that's the kernel. Now I want to think about the range for a minute. Maybe I need a little more room. Go back over here to do the range part, and then we're going to get a basis for the range. Do we know already what the dimension of the range should be? Yeah, so remember the general rank nullity theorem. The dimension of the kernel plus the dimension of the range adds up to the dimension of V. And this is V, which is 4-dimensional, right? And by the way, this is 5-dimensional here, right? So we do know that the dimension of, just going to write the general formula here again. This is really important. I can't imagine this won't be on the test somehow. This general rank nullity theorem is kind of, we've used this so much. It's a pretty big deal. So let's just get that up there as well. So we already know that this one is 0. From what we did a moment ago, we don't know this number yet, but the dimension of V is 4. So we can use this equation to figure out what the dimension of the range should be, even before we figure out what the range is. So we have 4 here. Now, do you guys remember how to do the range of T? Audrey, go ahead. Couldn't have said it better myself. We take the span of the transformation of a basis for V. So I look at that V here, M2 of R. Now, of course, there's 5 billion different bases for M2 of R. We can pick any one of them that we want. We don't have to be limited, but there's a nice one that might make our calculations easier, which is what we call the standard basis for the M2 of R, which would just be the matrices that have zeros in 3 out of the 4 spots and a 1 in one of the other spots. So I could just list these out. This is just my first step here to just kind of write out what this range would be as a set. So it's just T of the standard basis for M2 of R. Again, any basis would be acceptable. But if I want, I could make the choice to make the easiest basis that I know and love. Okay? And so then you actually have to calculate these things. So we have to calculate what is T of 1, 0, 0, 0. So I come back to the formula they gave me, and I put in a 1 for A, a 0 for all of the other variables. So on the right-hand side, if I put in a 1 for A and a 0 for all of the other variables, it looks like I'm just going to get 1. It's technically it's 1 plus 0x plus 0x squared, 0x cubed, and 0x to the 4th. Right, okay, so we have that. Now let's do the second vector, T of 0, 1, 0, 0. This means I'm going to put a 1 everywhere I see a B. I see several B's here. Everywhere I see a B, I'm going to put a 1 down, and all the A's and C's and D's just become 0. So what is that going to give me? 1 plus x squared plus x cubed plus x to the 4th. And guys, if anybody's not clear on how I'm getting these things, please ask me, because I do sometimes find students are not sure how I'm coming up with this. I'm basically just putting in numbers for A, B, C, and D right now to evaluate this thing. Right? Okay, what's the third one? T of 0, 0, 1, 0. I'm going to find where the C is, and everywhere there's a C, I'm going to put a 1. So I get a 1 on the constant term, a 1 on the x squared term, and a 1 on the x cubed term. Okay? Finally, I have to do T of 0, 0, 0, 1. So I look here, do I see a D anywhere? Wherever there's a D, I put a 1. All other variables are 0. So if D is 1, I'm just going to save that x cubed term, and that's it. That's it. Okay. Now that's what the range of T is. It is the span of these 4 polynomials. But the question is asking me to find a basis for the range of T. So the range of T is the span of these 4 things, but I'm being asked for a basis for the range of T. How do I get that? See, Evan?
Wait, sorry, what was the question?
The question was, how do I get a basis for the range of T?
Oh, yeah.
Never mind. Okay. Julia?
Matrix.
Okay, so these vectors are already going to span the range of T just by the way the range of T is constructed. What Julia said is we need to make sure that they are actually a basis by testing for Li. Okay. Do I really need to do that here? No. I actually get away cheap on this one. Do you know why?
It's 4 dimensional.
We already know the dimension of the range of T is 4. So this is the correct number. If these vectors were LD, we would be throwing some of them away to get our basis, and then our basis would be smaller than 4. Well, we know that shouldn't be true, right? This should be 4-dimensional. So guys, this is our basis without even having to break a sweat, right? That's the basis for the range of T. Now, there would be nothing wrong with doing what Julia said. Like we could put these vectors into a matrix. It's not a bad review of chapter 4, right? To go back, we could put them in the columns of a matrix and we would find out that there's no free variables. And that means the vectors are Li. They really are going to be a basis. Okay, so yeah, that's my basis for the range of T. And the only thing left is to decide, is T 1-to-1 onto both or neither? Do we have any thoughts on that from what we have so far? Evan?
It's 1-to-1.
Gonna be 1-to-1, isn't it? Right? Make sure you know your definitions here, guys. 1-to-1 just means the kernel is 0. So, by the way, even before I do any of this work, the fact that this is a 4 and this is a 5, the fact that V is smaller than W tells you even before you take a breath that it cannot be onto. You remember that? We got those 3 bullet points. If V is bigger than W, then T cannot be 1-to-1. If V is smaller than W, then T cannot be onto. And if V and W are the same size, then it's both or neither. Right? So in this case, V is smaller than W, so guys, it cannot be onto. And therefore it cannot be both. Even before you take a breath, you know that much. If you've got 30 seconds left before you have to turn in your exam and you're like, oh my gosh, I can't finish this problem. In 30 seconds or less, you can figure that much out and get like half credit on that question. Like, is it 1-to-1 onto both or neither? If you cross off the 2 wrong answers, that's great. I would give a little reason here. You cross this off since the dimension of V is less than the dimension of W. It would be good to write that down at least so we understand the reasoning behind it. Onto just means, just so everybody's getting clear what they need to know, onto would have meant that the range of T is all of W. But W is 5-dimensional and the range of T is only 4-dimensional. So it's not going to be onto here. But 1-to-1, as Evan just said, it is 1-to-1, right? Because the kernel of T being 0 is really what 1-to-1 means. And so here we've checked that already, right? The kernel is just the 0 vector. And so this one is 1-to-1 based on the calculation there. The 1-to-1 part is a maybe. If V is smaller than W, then it's a maybe on the 1-to-1. We have to actually work out the kernel to decide that. And here we've done that and we see that we get 0. Okay. So you know what, guys? I am going to, because I want to go take a dinner break before my office hours tonight. I didn't actually go over the extra credit quiz, but I have done 6 problems here that I think you should now, especially if you didn't do very well on the extra credit quiz, I think you should go. I have a blank copy of it in the midterm 3 resources folder. Print it out again and see if you can get 100% on that thing. The solutions are there, the questions are there. I bet if you've paid attention to this review, you can ace that extra credit quiz. If not, I've got a lot of office hours later tonight, also tomorrow. Shoot me emails, whatever I can do to help. I'm so stoked that so many of you took time out of your Sunday to come down and hang out today and do some math with me. But I think I'm going to go ahead and call it a day if that's all right with you.